And what I'd like to provide to you is an update on what we've been doing in Stream 1. So, I've been talking about Stream 1 like loads of times in lots of different formats and forums, etc. But what I want to do is start bringing together all of that geochemical, mineralogical and laser ablation data that we've been collecting and start to build that understanding in terms of linking the ore deposit types to what we're seeing in the waste. And obviously this is a 4-year program. We started in 2020 and we finish in 2024. So, this is a work in progress. So, as we characterize more sites, we'll be able to build on this knowledge. But I'd like to just share today with you some of the work we've been doing around the state. So I showed this very briefly earlier, and certainly it shows kind of the 16 main sites that we've been out and sampled already. So after, I guess, after this week and the next, Laura, myself and the rest of the team will be going back out and sort of starting our next round of campaigning, obviously very well timed with the Queensland summer. But obviously we'll be adding to I guess, this general list. But in terms of where we've been already, some of those might be familiar to you and some of those might be sites where you'd like to get a bit more information. And if it is the case that that's what you're after, then we have 14 completed reports that are available through the GSQ portal. If not now, they soon will be. But on top of that, what we're preparing are a series of individual seminars or webinars on each of the different studied sites that we've been working on, and we will be intending to upload those to our SMI website. So it's a place where you can go, you can sort of learn a bit more about what we're doing interactively, and we can talk through the results and what they mean. Certainly isn't the time to go through all of those 14 or 16 sites today, but we'll give sort of a good overview in terms of what we've been doing. So we've talked about a few different waste streams. Certainly there's a lot of different waste types to sample. Today, our focus probably has been on waste rock and tailings. And I guess I just wanted to list here sort of the sites where we've kind of tackled one or two different waste streams at a particular site. So for example, you'll see Capricorn copper kind of features on both of these lists. Places like Pindora, there's a little bit of waste rock there, but there's also some spent heap leach materials and so forth. But that's just to kind of give you a snapshot of the diversity of what this project is now looking at, because in each of those things, there's potentially something valuable there. And when we're thinking about waste rock and we're thinking about tailings in particular, we know those are the things that are, considerably, they can be sulfide bearing, and we can have things like acid and metalliferous drainage forming. And that's certainly not what we want to see. We want to sort of try and adopt economic rehabilitation processes which enable us to turn those sites around and actually derive value from waste. But there's also been some pretty interesting weird ones that we've had the opportunity to go and sample. I certainly remember going to Phosphate Hill and sampling some of the slime dumps and the phosphogypsum waste. That was by far my least favourite. But these things have got to be done, and actually it was very much worth doing because we were evaluating the rare earth element content of those particular waste materials. But in terms of where to next, I'm just going to say it now because who knows if we get to the end of this particular talk. But there's a lot more opportunities out there. We've seen across sort of the sector, more and more people are starting to look at those bauxite residues in terms of the recovery of the rare earth elements, also gallium and germanium. It's probably a bit more advanced in North America and Europe. I've certainly seen some good case studies coming out from those particular areas. But also, if we think about down in Tasmania, for example, there's been the characterisation of the bauxite residues down there for rare earth element recovery too. So we've got that opportunity too to continue to build here in Queensland. Certainly, Rio Tinto have been looking at theirs and so forth. But there's a lot more opportunities to get into that space, and certainly looking at coal mine waste as well. There's opportunities again to look at rare earth element recovery, gallium, germanium, and selenium. So I guess as the program continues into the future, these are probably some of the other waste streams that we would like to consider bringing into the fold. So that's just to give you a bit of a snapshot of what we've been doing. And, we mentioned it briefly before in terms of what the analytical program looks like. I've probably said it to many of you online already, but if you're sort of new to sort of what we've been doing here, what we do in Stream 1 is we go to a site and we collect the samples using the methods that Laura talked about, and we put it through a geochemical assay program. And so we sort of look at analysing sort of, as many of the periodic table as we can sort of within the budgetary constraints. And then, if we've collected 80 samples, we'll cherry pick kind of the 10 most endowed in the new economy metal that we're chasing, and we'll subject those to very detailed MLA and XRD and laser ablation ICPMS studies to really understand the mineralogy and the deportment of the target phase. Because there's, you can assay things, which is great, but unless you actually understand how the element of interest or the metal of interest is mineralogically hosted, then you will not optimize your recovery. So, I mean, it's very much speaking to the classic principles of geometallurgy. You know, geometallurgy is about optimizing value. And so in order to optimize the value from this waste, we have to adopt that kind of lens. So these are absolutely crucial to include into your program. And if you've got the opportunity to, you know, tools like MicroXRF, as Lauren talked about, it's great to be able to take some of those waste materials and, you know, really look at that textural component on a different scale. So MLA certainly is operating at that micro scale, but to sort of start coming out, you know, looking at core scale features, because obviously how the micro and the meso relate to each other is quite important when you start to think about actually, you know, breaking the rock open and undertaking that sort of metallurgical process. So, you know, we've sampled 16 sites to date. We've got 14 complete reports, but we have another 21 planned for the rest of the program. And we've also got the additional opportunity to do at least 4 additional Stream 1 sites as funded by Geoscience Australia within Queensland. And so we've got, you know, the potential to do another 4 within or outside of Queensland, but 4 definitely will be within there. So we're going to start building up a very significant body of knowledge by the end of this program. So I'm sure all of these slides will look very different at the end, but certainly this is a synthesis of where we're at now. So when we kicked off the program, I guess when Helen first talked to me about this, the main focus was on cobalt. So a lot of what I'm going to talk to you about now is very much going to have that cobalt flavor. And we do get that question a lot. You know, we go to, you know, webinars or mixers or conferences if they're allowed. And people sort of stop and they say to us, well, why are you bothering with cobalt? Because, you know, there's lots of cobalt coming out of, you know, the DRC. Why would you even bother looking for cobalt? There's no value in chasing it. But actually, I disagree with that quite fundamentally. I mean, we look at the Ernest Young risks again, we think back to those, and, you know, those environmental factors are sort of dominating the risks in mining. And so certainly thinking about, you know, new ethical sources for cobalt, that could include through economic rehabilitation. And certainly as we look at the price of cobalt over the years, you know, certainly it had a bit of a peak here in March 2018. I mean, that was staggering to think that it was up at 95,000 per ton US. That was pretty insane, but obviously it did take a bit of a drop. But we can see now we're sort of getting back to what looks like a growth phase for cobalt. And certainly things like a lot of articles coming out, you know, cobalt's changing landscape, and have people like Tesla and all the car companies kind of tapping into sort of wanting to get cobalt from beyond the Congo. There's this real opportunity to put under their noses, you know, well, how about considering this mine waste material as something where you can supplement the source of the cobalt that you need. So I think for us in the economic rehabilitation space, I fundamentally disagree that looking for cobalt is a waste of time. It absolutely isn't. And if we start thinking about where we should be looking for cobalt, I mean, there's obviously been a number of review papers come out, and I quite like this one. Obviously they're based on Gavin's stats. So Gavin, if you're online, I hope these are all correct. But yes, certainly we start thinking about relating that ore deposit type to, you know, where potentially the cobalt could be rich in the waste. And, you know, here's a good sort of starting place in terms of where to go from. So, you know, here I've pulled out stratiform sediment hosted, copper cobalt deposits, you know, metasediment hosted cobalt, copper, gold deposits, VMSs, IOCGs. These are all places where we should be looking. And certainly within Queensland, we have lots of examples of, you know, mined deposits, you know, places where that mine waste already exists, where you can actually go and start looking for these minerals. So it's an exciting time indeed. And so if I just show you a summation of, you know, some of the results from cobalt and our exploration there, just looking at the whole rock assay data, we can certainly see we've got a decent concentration around the northwest. And that certainly, you know, aligns with sort of the IOCG, sediment hosted, and the epigenetic copper systems that we've got there. So certainly these, you know, these significant operations we've got there, looking in their mine tailings for cobalt is definitely looking like a potentially economic prospect. I mean, some of you might be thinking, well, for an assay grade, well, that's probably actually not very high. But actually, if we think about some of the mining projects that have been mined overseas, you know, the grade has been a little bit lower. And I think we were talking to a Mets company, Helen and I, and they were basically saying that anything that's probably 300 and above ppm average is probably something that's worth considering. And so if we kind of think about that mentality here, we can certainly see, you know, within Queensland, we've got, you know, at least Rocklands and Osborne definitely sort of fit that criteria. But the other important thing to think about is where is that value hosted? And so, you know, pairing the assay result observation against, you know, an understanding of the mineralogical host is absolutely fundamental. So not very elegantly, but what I tried to put out, sort of highlight here was kind of within these different mineral groups or mineral types, you know, they're different hosts for cobalt. So somewhere like Pindora, for example, which is a small former heap leaching operation, I guess in the Kalman region, we can see that cobalt is basically spewed into everything. It's in the sulfides, it's in, you know, the secondary iron oxides. It's also present in the carbonates, which is interesting. And, you know, if we look at more of our IOCG type deposits, we can definitely see that cobalt's hosted in pyrite. It's also hosted in pyrrhotite. And these are in a lighter grey colour because they're not secondary iron oxides, but it was also hosted in magnetite. So, you know, by understanding the different phases that it's hosted in, we can actually optimise that recovery, which kind of speaks to that geometallurgical approach. And so, you know, I showed you this one here, where this was kind of the average cobalt based on the whole rock. But if we actually think about upgrading this and actually thinking about laser ablation and the mineral chemistry, so I've told you here which mineral phases they're hosted in. But if we look at the mineral chemistry and the cobalt content within those, we can sort of start to see the grades suitably increase. And so now, somewhere like Rocklands on average has just under 1% of cobalt, which goes to show that sort of undertaking that concentration phase and then, you know, the recovery phase, you know, there's certainly value to be had there in terms of looking at a serious cobalt project. And so if you wanted to sort of look at that on a graphically, you know, that's what we've shown here. So we can see, you know, the grey bars, they speak to the whole rock values, but certainly we can see from the laser ablation of the individual sort of minerals that host the cobalt. So this is obviously a mix of pyrite and iron oxides and so forth. We can certainly see that, you know, yes, at Rocklands we have a significant upgrade if we just look at the, laser ablation mineral chemistry data. And very much, again, it's those IOCGs that have that really strong cobalt signature. And so just to dive into that a bit further, you know, this is work that Shinova actually undertook themselves. So they were intrigued as to what their cobalt content was in their TSF. So they did their own in-house sampling campaign, and they've sort of given us permission to share this. But certainly, you know, within their TSF1, you know, the average grade of cobalt that they measured was 856 ppm. So the data we presented was based on the samples that we took as a subset, but the whole total sort of, I guess, value is 856 ppm, which is pretty good. And certainly for TSF2, we've got 582 ppm, and over for the cell wind tailings, so it's considerably lower. It's 114 ppm. But again, if we start thinking about, you know, just the production of the concentrate and the upgrade factor of the cobalt, then we can see that we're sort of starting to talk serious numbers there. And we think about the mineralogy of these materials. You know, we've got iron oxides, we've got quartz, we've got iron sulfides, and that's both the pyrite and the pyrrhotite. And we've got a range of sort of silicate minerals as well as that sort of are associated here. It's not a strong point that we're making sort of in this particular project per se, but certainly if we're going to go down the pathway of valorization, then these sort of non-sulfide gang phases are really crucial, because we need to start thinking about what we could do with them. If we're going to go through the process of rehandling, is there something we could do with that quartz, for example? I mean, obviously you heard a few weeks ago from Katerina Savinova sort of thinking about silica deposits, but, you know, is there an opportunity here to recover that quartz and use that, you know, in future products? So there's all sorts of opportunities here. It doesn't necessarily just have to be with the critical metal or the new economy minerals in sort of main focus in that regard. And so if we dig a bit further into that sort of mineral chemistry, again, we sort of highlighted that there was significant value, but I said that it was in the pyrite, the pyrrhotite, and the magnetite, and that sort of is just really representing sort of the variability within the three phases. So, you know, undertaking magnetic separation, recovering that magnetite, and, you know, looking to recover the cobalt could also be something that's potentially valuable. So I guess it's you know, it's the point that I'm making here is that, you know, obviously when you're undertaking the mineral chemistry, it's good not just sort of just to make an assumption that it's in just the pyrite, which anecdotally is what we'd heard. It's just in the pyrite, it's just in the pyrite. We did laser ablation on a couple of other phases and found actually there's a sniff in other minerals. So it's good to sort of be holistic. And the tools that Lauren and Olivia were talking about in terms of doing that characterization on sort of solid materials at the drill core stage can really help to inform those decisions we make when we start to look at waste exploration. So it's really important to link both things together, because it's all part of the, I guess, the same system, as it were. And certainly we see that signature again for Selwyn too. You know, we were asked, you know, it's an ICG, so is there gold? Yes, there's a sniff of gold, which we also did resolve in our investigations, but we're not going to focus on gold too much here. But certainly there was a little bit of gold to be recovered potentially too from this material. So I guess it's always thinking about what else could you get out of this potential mineral if we're going to go through reprocessing, and that needs to be built into that thought process of the eventual flow sheet that you build. And so based on that information, it's kind of exciting. So what's happened now is we've now been able to talk to Osborne about obtaining some materials to do some further test work in Stream 3. And so we haven't talked much about Stream 3, but Anne will in the next talk. So Stream 3 is where we're doing our metallurgical processing. So they very kindly recovered some bulk materials for us. And again, if we show that sort of upgrade factor, what our intention is to do is to, you know, produce, to undertake flotation work on the materials, and we'll do that with our partners here at the JKMRC, and we've literally just got a report in assessing the viability for that, and we can certainly see how we can actually optimize that flotation work. And then, you know, paired with our colleagues over at the School of Environmental and Earth Sciences, we're going to be looking to sort of undertake some bioleaching approaches to actually recovering that value. But in parallel, you know, we've certainly been talking to Cobalt Blue about sending them some of this bulk sample material and testing it through their process. And certainly the METS companies have a really key role in helping us drive this kind of change forward, because obviously there's been a whole spate of new technologies developed sort of with a focus of tailings reprocessing and waste reprocessing in mind. And certainly through the collaboration in this project and others, there's that opportunity to actually really take the characterization into, you know, different labs and really upscale what we're doing. So that's what we hope we can continue to do. And we certainly hope we can continue to do this here at Rocklands. And so Rocklands, I suppose, has been in the media a little bit this week, and we'll talk about that a bit later on. But certainly we had a first sniff at the Rocklands tailings in 2020. And obviously in my chart of cobalt across the state that we'd sampled so far, this was our second most endowed. We can see, you know, in the sort of limited time we had on site to sample, and this was a hand-auger campaign, so just shy of 10 on this one. But certainly we can see here that we've got cobalt up to about, you know, just over 1,000 ppm in this particular hole through, which is pretty good. And when we look at copper grades, they don't quite pair to the cobalt. So when we look at some bivariate plots of cobalt against copper, they don't quite, you know, the R square and the correlation isn't quite as strong as we'd hoped. But certainly we can see there is opportunity to, if we think about reprocessing, to also think about what we could potentially do in order to recover additional copper from these materials too. You know, in terms of where our cobalt was most endowed, it always pays to sort of log things in detail. And so we identified a particular horizon, which was dark grey sandy tailings. Knowing things like that and the mineral properties are super important too when we start thinking about that mineral processing suitability. And again, Anne will talk to you about that in her talk just after this. So we did a little bit of work kind of looking at the mineralogy and the mineral chemistry. Again, as I sort of previously said in that summary slide, you know, our pyrite was our main host for our cobalt, as we can kind of see here. You know, we had within the pyrite, we had up to, you know, 3 weight % cobalt, which is pretty tasty in my opinion. And that was great because those results went back to the government, and obviously Helen and her team sort of been discussing this with other organisations, including JOGMEC. And, you know, this week it was announced that, you know, they'd be partnering with the department and with ourselves to actually continue investigations at this site. So this is Torben Westerman, who's a PhD candidate here at the BRC. He was out augering the remaining holes that Laura and I weren't able to access on our trip. And that material now is coming back to Brisbane for further characterisation work. And we'll be undertaking that characterisation, that metallurgical testing in conjunction with JOGMEC too. So we're quite excited about what's to come. Stay tuned, because I think we're going to be sort of finding some new methodologies to recover this value too. We're also looking at another method through a complex ore bodies funded program that's being developed here. So I think there's a lot of things on the cook in terms of thinking about how we can recover the value from this particular site. And I guess it's not just the cobalt there to be won. So the other things that you could potentially find include, you know, cobalt and nickel. I mean, it's no secret that cobalt and nickel, you know, commonly coexist in these sort of pyrite phases. And it's no different when we look at the signature in these particular IOCGs. And certainly there's 2 clusters for Osborne, and that's because I didn't break out the pyrite and the pyrrhotite and the magnetite. So it can be, I probably should have done that, so sorry about that. But certainly you can see that in general, there's potential for additional recovery of nickel if we were going to go and recover the cobalt, which is also good because nickel's also on that new economy metals list that we need for that transition to the lower carbon future. If we look at cobalt against copper, we can see the trend's a little bit weaker. Certainly at Pindora, it seems like it's still sort of on trend. But, you know, I guess, you know, there is significant copper, as you can see, still in a lot of these sites too, particularly here at Rockland. So thinking about a process which will enable the cobalt recovery and additional copper recovery seems like a bit of a win-win to me. So I guess it becomes more complicated. Like, waste is not as straightforward as it may seem. And I guess when we think about where to next, I mean, we're basing our sort of current research on the fact that it's the IOCGs from what we've sampled that seem quite endowed. You know, we've been through sort of the department's list and sort of pulled out, you know, target sites which we think we should be sampling in the next round of target campaigns. So, you know, potentially, I'm just going to put it out there. There's potential to be global leaders in recovering cobalt from waste in this particular geological zone. I mean, it's a globally significant ISUG terrain, so why not be a future significant terrain for cobalt recovery from mine waste? I think there's good potential. Now, I mentioned copper a little bit, and so I just felt like I should probably talk about it too. So in terms of copper concentrations, it's no surprise that, you know, our most populated or our most endowed cobalt is in the northwest. But, you know, I think interestingly, it's the oxides materials. I mean, when I first started this venture, I guess I was more of a sulfide lady, but now I'm certainly very much turning my attention towards the oxide deposits that remain on site. So Mount Oxide was particularly well endowed in copper, as was Pindora, and you can probably see the copper right there in those waste rock particles that are on the surface there. So, you know, different thing, different waste rock. Now we're dealing with waste rock, but certainly still a lot of value to be recovered. You know, these are just some summary plots to show where the main concentrations of cobalt are, sort of around where we were able to sample, and copper too. And you can see there's probably a little bit more correlation in terms of cobalt and copper here. And here's just some hand examples of some of the materials that we were sampling. And so I suppose it's no surprise that things like this are pretty well endowed in cobalt and copper. But certainly in terms of cobalt endowment, it was very much in these more rusty oxide associated with sort of these secondary iron oxides and manganese oxides. So I guess that's probably what one would be looking for if they were going to look at recovery of cobalt from those materials. And so, yes, the cobalt was hosted in iron oxides at Mount Oxide, and copper was dominantly present in chrysocolla, azurite, malachite, brochantite, and cobalite as well. So, you know, a lot of different hosts there to think about. And certainly at Pindora, we saw something very similar. So very small site, but really cool, very hard to get to. So I think last time Laura and I went to site, we were with someone who was a former rally car driver, and we very much appreciated putting her in the driver's seat because it was pretty hairy. But what we can see here is, you know, spent heap leach material, waste rock dump. It's quite a small pile, you know, certainly not anything significant. But if there's a collection of these in a particular area, then collectively you could start to develop a business case for the rehabilitation of these materials. And so, you know, if we look at what we discovered here in terms of cobalt endowment, it was quite significant compared to some of the other sites. I mean, these waste rock particles up to 415 ppm, and, you know, compared to some of the tailings that we'd sampled in other parts, that's quite reasonable indeed. And certainly, as I said, the copper is also quite well endowed as well. So, you know, just to sort of quickly walk through what the sorts of things we found, you know, in terms of heap leach mineralogy, it was dominated by quartz, but the iron oxides were significant there too, and they've got a significant role to play in the cycling of cobalt in these environments. And certainly we saw a reflection of that in the waste rock as well. Okay, well, rare earth elements. This is something that's, you know, it's been very exciting. I don't think I was particularly into rare earth elements until I guess I started in this project, and now my mind is sort of quite fascinated by the opportunities that we have there. Certainly very necessary for the transition to the low carbon future. But, you know, in terms of what we found, we definitely see a concentration of rare earth elements in a north-south corridor along here. And I've just pulled it out just to make it a bit bigger because it was a little bit hard to see. But it's certainly interesting to see how this is concentrated. The places that really sang for rare earth elements in our studies, Mary Kathleen. So there's no surprise there. You know, we've been talking about Mary Kathleen as being a site where the tailings are endowed in rare earth elements for quite a few years now. So I guess it's good to see how it compares to some of the other sites we've got stuck into. And so when we start thinking about the mineralogical hosts of rare earth elements here, and I'm talking about them collectively, I'm not talking about individual ones, you know, we can see that there's a greater diversity in terms of the mineralogical hosts that we've been starting to pull out. So, I mean, obviously at Mary Kathleen, it was, you know, it's been widely reported allanite and stilwellite are the main hosts of lanthanum and cerium. If we think about Pindora and what I just said, you know, it's the secondary oxides and certainly the carbonates that seem to be endowed from the investigations that we've undertaken. Places like Wolfram Kemp, surprisingly, in our list, but we dig into the data and things like the iron oxides, the allanites, even the wolframite itself seemed to be, you know, potential hosts of the rare earth elements. And as we get sort of to places like Phosphate Hill, we see that transition towards more apatite hosts. So there's certainly a lot going on in this particular area. It's very diverse in terms of the mineralogical hosts, which is interesting. So if you don't know much about Mary Kathleen, it's a uranium rare earth element deposit located in the northwest. Its initial production between 58 and 63 was 2.9 million tonnes. Then had a second production phase between 76 and 82, where another 7 million tonnes of ore was processed. And it's important to know these things when you're starting to, you know, trawl back through a tailing storage facility, because all of a sudden you might see a really significant paleo horizon, or you might see, you know, a real textural change or sort of physical kind of difference. You might think, well, why is that? But certainly sometimes those reasons for those chemical and those physical differences are because, you know, the mine has been through this period of being operational and, you know, not operational. And so it's always important to do that desk study to understand a bit more about the site before you get stuck in. And so the critical metals of interest here were obviously rare earth elements. And so, you know, we had the opportunity to dig into some existing data, and that was from CSA Global. And looking at their assay results, you know, we just sort of pulled out the holes that they drilled here. We can start to see that in terms of percent of rare earth elements, you know, there's not too much to see in terms of trends, and certainly seem like it increases with depth, and I think that's fair. Certainly we've looked through all the logs and all the data, and it's definitely true that the grade increases with depth, and maybe that speaks to that change. You know, I said there was that first phase and that second phase of operations, and I think that's kind of like one of the signatures that we're seeing in that sort of depth variation of the rare earth elements. And I'm probably not going to talk about this in too much detail because I realise I don't have much time left, but certainly we did a lot of grade by size fraction analysis. So the CSA report kind of, you know, it tried to ascribe where the grade was, and we kind of wanted to look at, you know, is it really deporting to the fines? Because if it's, you know, the size of the host phase, you know, when we think about flotation work, it's really important. You know, if it's in the coarser grain size particles, then we can think about coarse particle flotation as a potential option to make that concentrate that we need. But if it's in the fine fraction, then obviously we need to use a different set of instruments and sort of cells and so forth. And so it's always really important to undertake this grade by size analysis if you're really starting to get into the serious realm of thinking about valorization of your tailings. And as I said, everything's dominated pretty much by lanthanum and cerium when we're talking about the rare earth element content in these materials. And speaking to that grade by size, that's kind of what we're looking at here. So for some particular samples that we took from the depth or from the deeper samples or the deeper depths of the tailing storage facility. So I suppose the maximum depth was probably just about 30 meters. And so we have sort of material from 26 meters depth, and that's obviously where the grade is higher. We can certainly see that there's, for the most part, there seems to be more endowment in the fine fraction, which is interesting to know then when we're starting to think about flotation methods to actually concentrate that. So we'd be looking at more a fine particle flotation cell. Here's some of the phases, the major phases and the key minor phases that could be potential hosts. And before I pulled out stilwellite and allanite as the main phases of rare earth element hosting, but actually there's a whole host more. So I guess when we started to get stuck into the laser ablation data, you know, there was a couple of spots that were misfired. You know, it's easy to do. You're sitting on the laser, you don't have a good microscope to, or the screen resolution of the spot you're doing, it's not quite clear, it's not quite, you know, it's a bit fuzzy. So, you know, there's misfires, but those misfires were really advantageous for us because what they showed us is that actually andradite is actually potentially also quite well endowed in our rare earth elements too, potentially. But certainly we see with a decrease in calcium concentration, we see an increase in the rare earth element content. So that's, I guess, if you don't have rare earth element data, like you don't have assay data, maybe you could sort of start to look at the calcium content as a way to sort of, as a proxy to help you understand the concentration. And so where is all this information led us? Well, it's, you know, Paul Gow and the team here at the BRC have been working on the rare earth element project with Helen and others. And our chemical engineering guys led by James Vaughan have undertaken some leach test work on this, and you know, they've developed a low temperature sulfuric acid leach methodology to enable the recovery of cerium and lanthanum in particular from these mine tailings. So I guess this is kind of where the research kind of helps sort of inform what the future decision could be around the valorization, the commercialization of these sites. And I guess where to next? And so I pinched this from Rick. He did an amazing talk a few weeks ago where he looked at rare earth element prospectivity. And I kind of think it's nice to see that, you know, this area here, this north-south corridor that we identified sort of very much correlates to where, you know, one of his hotspots were. I didn't really talk about it in too much detail. We did sort of have snips of rare earths up here, you know, with Wolfram Camp and so forth. But if we want to sort of think about where to next, then certainly there's a bunch of phosphate deposits where we can look at some of the waste materials. But there's also, you know, some rare earth element named deposits, again, where we could actually go back and start sampling that waste. And yes, it may not be a valuable prospect if it's a small deposit size, but I guess the point is if they're collected in one particular area, maybe there's a way to actually package it all up into something that does make sort of economic sense. So we heard about indium from Olivia, so I'm not going to talk about it too much. Certainly, the reason why her work is focused up in the northeast was pretty much driven by the fact that when we went out and had a bit of a look at indium deportment across our studied sites, certainly we see this concentration up here related to, I guess, the copper tin and the tin tungsten deposits that we have up in the northeast, and that's no secret. And I suppose I'm not going to talk too much about it, but certainly I guess when we think about what we could do at sites like this, Balgammon is by far our most endowed, and currently the material sits under that clay cap. But, how are we actually going to go about thinking about recovering the value? Olivia sort of highlighted that chalcopyrite seems to be pretty much where we should be looking if we're thinking about recovering that indium. Well, here's an opportunity to sort of find some METS collaborative partners and actually think about applying waste sorting technologies to a site like that. Because if we can actually, use XRF potentially sensor-based technologies to separate the copper-rich particles, then we can sort of really start to domain or, use those tools to sort of help us selectively remine, as it were, the waste rock materials there. So I guess it's like using these results to actually then test new technologies to help us realize the value. And again, thinking about where else we should be looking, then certainly there's a lot of places here that are in that northeastern region. And when Olivia gets here in January in the summer, we're going to be taking her out and sort of having a good old look around these sites to actually find some materials to sample, because we really do want to build that knowledge in terms of how indium actually cycles and moves in these mine waste environments, because there's not actually much literature on that at all. But certainly thinking about the other places we should be looking. I mean, Laura and I have spent a little bit of time down in Tassie looking, and Nathan too, looking at the indium content in sort of the West Coast deposits. And, we've got the, VHMS systems, but, there's an opportunity here to crack into these similar types of mineralogy. The VMS is up here in Queensland. So I think, when we think about additional indium exploration, we should be thinking about that too. And here's a map that just popped up, which I forgot was going to come, but certainly it goes to show that, yes, we've got opportunities here in Queensland, but certainly around Australia too. There's places where we should be looking for that indium in those VMS wastes, which are very reactive and, obviously have that potential for AMD generation, which is why they should be almost a priority target for indium recovery. Now, gold was one thing that we briefly looked at. I'm not going to labour on the point too much, except to say that, is your waste rock really waste? So this was a waste rock particle that we took at Horn Island. And here, so the average content sort of Horn Island was 2.1 ppm, which is quite significant. But certainly, this waste rock sample has got, 33.7 ppm gold. I mean, is that even waste? So I guess, go back and reevaluate stuff because you don't know what you're looking at. And, just to highlight the point about economic rehabilitation. So, I keep sort of saying rehabilitation, but certainly the thing that's going to drive the need to rehabilitate is if there's an environmental risk. And I think this is why I've shown this graph here. This is really important to show. This is a Ficklin plot. And so basically we've plotted net acid generation potential values against the summation of 6 key metals which concentrate in leachate. So you take these leachate measurements of those metals in the leachate derived from these NAG tests, and you plot them against each other, and you can start to understand the potential risks that the future leachate from that material could sort of have. And so we can see that in terms of the low-grade stockpile, we've got materials that fall into the high acid extreme metals. So it's going to show that there is a potential environmental risk in some of the waste types that we sampled at this site. And then if we pair that against where the potential value is, I mean, this is the waste rock dump, and the waste rock dump samples are in these red squares, so not too risky, I suppose. But certainly when we look at the the dam wall here, we've got some real hotspots of gold, and we've got some hotspots here in terms of environmental risk. So, it's always thinking about pairing it against the environmental assessment to really understand if there is a need to economically rehabilitate, which at that particular site there is, and there's that opportunity for gold recovery. Now, vanadium I know has been interesting for some people. Certainly for us, we had a look at it in the sites that we undertook. Didn't find too much in the way of significant value in terms of above cost abundance, but certainly we haven't really been exploring in this area. And, if we look at kind of these published examples of where the majority of vanadium resources sit in Queensland, perhaps we've just missed it and we haven't yet targeted that particular area. So perhaps this is where we need to be going to next, to actually start to uncover if there's, significant vanadium in our waste materials. For tungsten, again, that's one that's of common interest. And certainly, again, we see that concentration up here around, associated with the tungsten mines, which is really no surprise. And, when we start to actually dig into that, obviously Wolfram Camp was the site we sampled, and surprise, surprise, it was the highest in terms of tungsten assays in the waste rock dumps and the tailings that we sampled. But, you know, if we look at some individual particles, you know, this is a waste rock particle, you know, 4,500 ppm tungsten contained in that, and that was within wolframite. But then we actually started looking at the laser ablation data for wolframite, and we could see that, wow, this wolframite's like really jam-packed with lots of goodies. So I suppose it goes to show that actually don't just assume that the mineral chemistry of something is, you know, don't just assume because it's wolframite, I'm only going to look at tungsten. Actually undertaking that mineral chemistry might actually reveal that you've got other things in there that could be potentially interesting to trace too. Molybdenum, that's the final one that I think I'm going to talk about, but certainly, again, Wolfram Camp was a place where we saw the most molybdenum. And certainly we had a laser ablation analysis sort of, well, we undertook laser ablation on these materials too to look at rhenium concentration, and it was significant. I'm not going to share that, but certainly, again, it's like, you know, that may not be sort of the primary thing that you might be tracing, but certainly thinking about the value that could be associated with the molybdenum through rhenium is very significant too. So yeah, just keep your eyes open. And so I quite like this figure. This is something that Anne put together, I think is into 2020 or 2021, but certainly it goes to show that, you know, in terms of new economy metals, yeah, there's a whole bunch of waste stocks we should be looking at. So, you know, certainly in Stream 1, we've started on our journey in terms of characterising this, but we've got a lot more work to do to really sort of unlock the full potential of all of the different wastes that we have within the state. And so in summary, we've characterised 16 sites. In terms of a main cobalt focus, which is what we've had today, we've certainly got significant projects moving forward in the Osborne, the Capricorn copper, which I didn't talk about because Lauren talked about in the webinar last time, but obviously her PhD research has been focused on the characterisation of cobalt at Capricorn. A lot of significant results to come out of that in the next little while, and certainly Rocklands too. With these partnerships with METS and international organisations, I think we've got that real opportunity to really understand if we can recover that value. And so, yeah, I think that's probably where I should leave things, but I just want to say thank you very much for listening. If you've got any questions, I guess you're going to have to put them in the Q&A box because we're getting tight for time, but it's certainly been my pleasure to share this with you today. And if you've got any questions, just feel free to contact me at any time.